One interesting thing about geometric sequences is that we actually also have a sum formula for the sum of an infinite geometric sequence. An infinite geometric sequence. That means the sum of an infinite number of terms. If the absolute value of r is less than 1, meaning the absolute value of our common ratio is less than 1, the sum of an infinite geometric sequence is given by the formula S is equal to A1 divided by 1 minus R, where A1 is the first term in the sum and R is the common ratio. Now, this only applies if the absolute value of the common ratio is less than 1. If the absolute value of the common ratio is greater than 1, then we are not going to have the sum of that infinite geometric sequence. The absolute value of r must be less than 1. And let's think a little bit about why. Here is our sum formula for the sum of a finite geometric sequence. Well, for the sum of an infinite geometric sequence, essentially n is going to be approaching infinity, right? We are adding up an infinite number of terms. Well, if the absolute value of r is less than 1, let's think about what happens as we raise it to a larger and larger power. Think, for example, real quick, 1/2. If I take 1/2 and I square it, we get 1/4. If I take 1/2 and I cube it, we get 1/8. If we take 1/2 and we raise it to the 4th power, we get 1/16. So what happens as this exponent gets larger and larger and larger? The values get smaller and smaller and smaller. What this is saying is that if the absolute value of r is less than 1, and we raise that to a really big exponent, this term essentially approaches 0. As n goes to infinity, the number of terms we are adding goes to infinity, r raised to the nth power is going to approach 0. If we plug in a 0, well, 1 minus 0, that just gives me 1 in my numerator, and I can multiply this a1 in, leaving me with a1 divided by 1 minus r. Notice that is our sum of an infinite geometric sequence. So, you might be thinking, how is it possible for the sum of an infinite number of values or terms to not be positive or negative infinity? Consider the sum from I equals 1 to infinity of 1/10 raised to the I power. This is a geometric sequence because our variable I is located in the exponent, but let's just think about what the terms of this sequence would be. To find the first term of the sequence, I would plug in 1 for I, and plugging in 1 for I, well, 1/10 raised to the 1 gives me 1/10. The next term of the sum, I would plug in 2 for I. 1/10 squared would be 1/100th. To find the third term, I would plug in 3 for I. That gives me 1 over 1,000. And then I would get 1 over 10,000, plus every other term until we get up to our infinite term, right? We would be plugging in terms forever and ever and ever. Well, let's think about each one of these fractions. 1/10. 1/10 is the same thing as 0.1. And 1/100th is the same thing as 0.01. And 1/1000th is the same as 0.001. And 1/10,000th is 0.0001. Plus every single other decimal. Well, if we added all those values together, we would get 0.111 repeating. And 0.111 repeating, well, that is actually equal to 1/9. So, when is it possible for a sum of infinite numbers to not be positive or negative infinity? The terms of our sequence, all right, the terms of the sequence a subscript I must approach 0 as I goes to infinity. Notice that as our value of I gets larger and larger and larger, the terms get closer and closer to 0. All right, so this only works if our terms get closer and closer to 0. Our terms will get closer and closer to 0 if the absolute value of our common ratio is less than 1. Okay, so that's very important. This only applies when the absolute value of r is less than 1. Let's see a couple examples. Find the sum using the proper sum formula. Well, right off the bat, we see that this is an infinite sum. we see that our variable n is located in the exponent, we want to use our sum formula for an infinite geometric sequence. S is equal to a1 divided by 1 minus r. Well, we have to know what the first term in the sum is. This sum begins with n equals 0. To find the first term, we plug in 0 for n. 2 times 2/3 raised to the 0. Any non-zero number raised to the 0 power gives me 1. 2 times 1 gives us 2 as the first term in the sum. We also have to know r. R, again, is whatever value is being raised to the exponent. In this case, the value that's being raised to the exponent is 2/3. So we plug that into our formula. S is equal to 2 divided by 1 minus 2/3. Well, 1 minus 2/3, that's 1/3. And 2 divided by 1/3, dividing by 1/3 is the same thing as multiplying by 3. 2 times 3 gives us 6 for our final answer. Yes, if we were to take every single term in this sequence and add them all together, we would end up with 6. Let's try another one. The sum from I equals 5 to infinity of negative 1,000 times 1/5 raised to the I minus 1. Again, the upper limit here is infinity. That tells us that this is an infinite sum. Because our variable I is in the exponent, we know that it is geometric. This is the sum of an infinite geometric sequence, which is equal to a1 over 1 minus r. A1 is the first term in the sum. Well, looking carefully at this summation, it begins at I equals 5. That means the first term in this sum would be obtained by plugging in 5 for I. So we plug in 5 for I, negative 1,000 times 1/5 raised to the 5 minus 1. We type that into our calculator, hit the math frac button, and we get negative 8/5. That is the first term. R, our common ratio. The common ratio is always the value that is being raised to the exponent. In this case, r is equal to 1/5. And once we have those numbers, we can plug them into the formula. S is equal to negative 8/5 divided by 1 minus 1/5. Well, 1 minus 1/5, that's 5/5 minus 1/5 gives me 4/5. Negative 8/5 divided by 4/5, same thing as multiplying by 5 over 4. Negative 2 is our solution. Okay, one more here. Find the sum of the given sequence using the proper sum formula. We have 9, 6, 4, 8/3, comma, dot, dot, dot. Now this dot, dot, dot here implies that we are dealing with an infinite sequence. Well, we only have sums of infinite geometric sequences, so we can kind of guess that this sequence is indeed geometric. That means we want to use our sum formula for the sum of a geometric sequence. S is equal to a1 divided by 1 minus r. a1, that's the first term in the sum. Well, what would be the first number that we are adding up? In this case, because we have our list of terms, we know that a1 is going to equal 9. R is the common ratio between our terms. Well, we don't have the sequence written out, but we do know that geometric sequences have a common ratio, and that common ratio is found by taking one term and dividing by the previous term. In other words, I could take 6 and divide by 9, or 4 and divide by 6, or 8/3 and divide by 4. And all of those must give me the exact same value if the sequence is geometric. And it is. All of these reduce into 2/3 for our common ratio. So now that we have a1 and we have r, we plug them into the formula. S is equal to 9 divided by 1 minus 2/3. 1 minus 2/3, well, that gives me 1/3. 9 divided by 1/3, dividing by 1/3 is the same as multiplying by 3. 9 times 3 gives us 27 as our final answer. All right, so there we have it, the sum of an infinite geometric sequence. Again, this only applies if the absolute value of r, of our common ratio, is less than 1.